Let us continue our discussion on double integrals. Okay, so we had discussed two examples, okay, for double integral and one example for I think triple integral. And what we had done basically so far, we have done that certain functions we can talk about the double integral over rectangle and triple integral over box, and then we saw that Fauvenier's theorem helps us to compute those, isn't it? Okay, so now I am going to consider another example in this line, and suppose that we are asked to compute this double integral d, the domain is d, and what is this domain? This domain is bounded by these lines which are joining these 3 points, so 0 0 1 0 and 1 1. Okay, so we look at this. Okay, so first we need to see function is explicitly given. What is the domain? So the domain is look at the lines which join these 3 points. So when I have only 3 points, I am not going to get a rectangle. Okay, so we immediately notice that the given domain is not a rectangle. Okay, so that is the first thing, and so far we only know the double integral over a rectangle, isn't it? So this is a problem which doesn't look like in a straightforward manner that what we know. So we have to think about it, how do we solve. Okay, yeah, so therefore as I said, we do not know how to evaluate this double integral immediately. Okay, so just try to draw things up. Okay, so as I am saying over here, that if we are a little bit careful, we will see that the domain is precisely half of a rectangle. If I get one more vertex here, this vertex here I have 0 0 1 0, and this was missing. So if I take this 0 1 also, then I can get a rectangle. Okay, but your function is only given on this, but since this function is x plus by whole square, this is defined for anything, and more importantly, this function is symmetric in x and y. So when it is symmetric, and if I take a symmetric domain in x and y, then there's a chance that what I get, it's not going to give anything extra in the sense that if I compute the volume over or compute the integral over this rectangle and then divide it into 2, I should get what I am asked to. Okay, so look at the picture. I have a picture over here. So the domain is okay. So I mean, right now we have to just look at the square part. So the domain is given this, because these are the 3 points, and the domain is bounded by these lines. Okay, so the domain is this for the problem, and what I am saying that you extend the domain to this so that it forms a rectangle. Okay, or here it is actually a square, but square and rectangle we know how to deal with. Okay, and since the function is symmetric, so there is a chance that if I compute the double integral over this whole thing and then take half of it, I should get the required thing. Okay, because the problem is coming from the fact that we do not know, we have not given a definition for double integral over a triangle, for example. Correct? What we have done, we have the definition of double integral over a rectangle. Okay, so this is a very natural situation, that why should all the time the domain should look like a rectangle, a perfect rectangle. Okay, so basically this tells us that we should be able to address volumes, or we should be able to compute volumes where the domain is not really a rectangle. Okay, so here the problem is in a way simple, which intuitively tells us that from this triangle we can go to a rectangle. Okay, and then we solve from our previous definition. But the problem can be made a little complicated. This idea may not be able to help us if I just change the problem a little bit. So instead of this 1 comma 1, suppose I had taken the point 2 comma 2. So let's say instead of this triangle, if I had this triangle. Okay, now this line is also not at the right angle. So now the triangle is this. If this was the domain, can I use the same idea that go to a rectangle? it doesn't look so immediately, because it will require more work, because you have to first complete this one, but then also you have to do something over here, okay, and then you have to figure out that how much extra you are computing, and so on, okay. So that may involve several steps, but geometrically this is just a triangle. So the idea is, like, can we have a situation, or can we have a result which allows us to compute double integrals over these kind of domains without really completing, or without really going to the rectangles, which so that is the problem we are going to take in our hands, and then we are trying to develop or extend the definition of double integrals to this kind of domain, okay. And not only this, actually we can allow that these need not be straight lines, these can be also curves over here, okay. So we are going to get a much general picture for which we can compute the double integrals. All right, okay. So this is the notion of double integral over slightly more general domains. I have written general domains, but this is not the best possible scenario, okay, because that is something which is not clear how to do it. All right. So what we do, we take a function which is defined over a bounded domain, okay. Bounded domain we have to compute, we have to take, because integration over bounded things we will be doing only, okay. So what we can do, since this is a bounded domain, we can always put this bounded domain in a big rectangle, okay. And what we do is we extend our function f, okay, this is a small typo here, through this big rectangle by just setting it to 0. So on D you say it is the same function as the given function, and outside the D in the complement of D inside that rectangle it is 0. So when it is 0, it's not going to contribute to the volume, correct. So what we do is that we define the double integral of f on this domain. I am not really giving any constraint on the shape of D, isn't it? And we say that this is the double integral over the rectangle of this extended function, okay. So this is very natural way, but every time we have to make sure, because now we have this function capital F here, which is been set to 0 on the complement of D inside this big rectangle. So one has to first make sure that this integral makes sense. This new function is Riemann integrable and so on. So if you can do that, then well and good, but we do not have any clear idea that gives us a guarantee that this can always be done, okay. So as I am saying over here, that there is no general method which will tell you that how to compute this, okay. Rather what we are going to do is, we are going to have these situations which I just described to you. So this extra work here is just to tell you that in principle you can define the double integral over any domain, bounded domain, provided these things exist, without really worrying about the shape of the domain, but we do not know how to go about it. All right. So rather what we can do is, with the definition which we had given over rectangles, and we try to just extend that, okay. So we are going to consider a more general form of Fubini's theorem, okay. So this tells us that suppose you are given a continuous function on a bounded domain D, okay. Now this domain, I am going to prescribe some conditions on this domain, and we will see that we can compute the area. So this theorem tells that I can compute the area I should not say, the volume which is given by this double integral, or I should say that I can compute the double integral over this domain, provided that this domain looks like this. It says that A varies between an interval and by varies between two continuous functions, okay. So one variable is varying on an interval, and other variable is determined by two functions of the first variable, okay, and these functions are real valued continuous function on the domain of X, okay. Then we can compute. So this was, if you go back, this was precisely the situation. This is a continuous function of one variable into the you can write y equal to something or x equal to something, whichever way you want to write. So here the variable, for example, let's say x is varying from all the way, because you have to drop perpendicular from here. So the x is going to vary from 0 to 2, and then y is varying on this line and y is varying on this line. So this is a function of x, this is another function of x, so y is varying between these two. Okay, you have to be little careful. I mean, this is not so straightforward. I should say x is varying between these two. Okay, so the precisely the situation is this, and we have basically allowed it more general, because we are not saying that lines okay, this is gone. So we are saying here that the domain can be determined by two continuous functions for a given variable y. Okay, and then I can compute the double integral. So what you do, you first compute this iterated integral, first perform the integration with respect to y, and then perform the integration with respect to x. Okay, so same thing can be done if the situation is reverse, in the sense that x is varying between two functions of y which are continuous, and y is varying over an interval. Okay, so just change of, so now you have to perform the integral with respect to x first, and then with respect to y. Okay, so both these kind of domains, which are much more general, correct, because the rectangle is just take these functions to be constant. So this you take a and this you take b, so this is going to give you the rectangle. So these are not only going to give you that the domains which are decided by lines, but also by just graph of continuous functions. Okay, so this is very general situation, and the Fubini theorem tells us that you can actually deal with this and compute the double integral. So the double integral is nothing but these iterated integrals. All right. So let us look for an example. One example I had already given to you. That example you can compute, but I am going to give you a few more examples, so that we have more things in our hands, so that we can verify things. All right. So question is saying that compute the volume of this solid under this paraboloid. Okay, and the region is in the xy plane, which is bounded by these two lines. Okay, sorry, it's one is line, other one is parabola. Okay, so this is easy. You can draw y equal to 2x, and then so this is the y equal to 2x line, and then the parabola y equal to x squared. So this is the parabola. All right, and the graph or the surface is given by the z equal to x square plus y square. Okay, so that is the surface. So that is the function you need to integrate. Now you see, the Fubini theorem, as I had told you in the beginning when we defined the Fubini idea of Fubini's theorem, that what we are doing, we are cutting the slices. We are cutting the slices in parallel to xz or parallel to yz. Okay, so again that thing you have to be careful, that when this kind of domain is given to us, that which kind of slice we need to consider. Okay, we need to decide whether the limits for x are going to be determined by these functions, or limits of y are going to be determined. Okay, so that is the crucial part here. Okay, so here this vertical arrow here, this is telling us that I am looking at these vertical slices. That means I am going to look for the limits of y determined by x. So I am fixing an x and then looking for the slices for vertical ones. Okay, and if I put an arrow like this, then you would be doing it other way around. Okay, so sometimes you will notice that taking the horizontal one or the vertical ones may not be possible. It may not be possible to take any of the two situations. So you have to decide which one is going to help you compute the volume or the whatever you are solving in an easy manner. So that will come when you have solved some problems. Okay, so look at these two, the curves, they intersect at 0 0 and 2 4. Okay, so as I said, I am taking the vertical ones. So the limits of the limit of x is from this point 0 to this point 2. Okay, and the limit of y is going to be from this curve to this curve. Okay, so you can just write down the integral. So this is y equal to x square, which was precisely this, and then this is y equal to 2x. So this is the integral which you need to compute, and this is an integral which you can easily compute. Okay, I did not even complete it, so you please complete it. But the point I am trying to make here, that you have to draw the picture and see that these two curves, whether we should consider the horizontal slices or the vertical slices, so that you have to decide depending on the problem. Okay, and this problem is such, we can do any of the two. I could do this, and then similarly I could have taken the limits for x in terms of y. So if I do that, then x is going to vary from y over 2 to square root of y, correct? This is from this line to the parabola, and then the limits of y will be now 0 to, now this is the 4, correct? So the limits of y are going to be 4. So often you should whenever it's possible, try to do it both ways, and try to see whether they are matching or not, so that way you verify the both the situations. Okay, and I have given you one more example which will kind of illustrate that you need to be a little bit careful. Okay, so this says that find the volume of the tetrahedron. So always these kind of problems will require you to draw the thing which you want to compute. Okay, and this is bounded by these planes. So all these guys you can draw. Okay, so I have precisely whatever I have written here is I am speaking. So you need to first determine, this is just some equations of planes, so you have to determine that which surface you are going to integrate over what kind of domain, correct? So that is the data you need to extract from the given wording of this problem. Okay, so this is clear that the surface is going to be is determined by this, and these are the planes. So you draw them, and then you see what is the part in the xy plane over which you are taking the integral. Okay, so I will straight away go to the picture. So this is the tetrahedron. See, I am taking these pictures from the book so that I can explain you easily. And this plane which is written over here, this is the plane which is defining the surface. Okay, and the plane x equal to 2y. Okay, now you see this is x equal to 2y, there is no z here. So look at this line segment, this is x equal to 2y in the xy plane, and what is it? This is like vertical, because for every z you have the same situation. So this is another vertical plane, and then what else you have in the, go back to the and then x equal to 0 and z equal to 0. So the z equal to 0 is telling you that you are in the xy plane, you are not going below that. Okay, so above the xy plane, and this is basically the tetrahedron you are interested in. Okay, and look at all these things. So now this plane, if you look at x plus 2y plus z equals to 2, this plane is going to intersect the xy plane in this line, and this line is precisely this x plus 2y equals to 2. So now you see that you have this line in the xy plane, this line in the xy plane, and then the line at the back, correct? So these three lines will determine the domain. So this is precisely the situation. Okay, so this is our domain, and you are integrating this surface so that you get the tetrahedron, isn't it? So here or in many problems, the part which is going to be a little bit tricky sometimes is to decide what is the domain you are looking at. Okay, the domain and the surface. Okay, so now this is the domain. So now again I have two ways to go about it. One is slice it horizontally and slices vertically. Okay, so if I am doing the vertical slides, so what I am getting is that the values of y, they start at this line and then they go all the way to this line. So this is a perfect situation, I can do that. And then the integral for x is going to be from this point to this point, which is 1, and y integral is going to be from this line to this line. So this is a situation which can be easily done. But instead of this, if I had tried to do this, what would happen? The horizontal ones, if I am doing so the the change in y is from 0 to 1, but change in x, there's going to be a slight problem here. You are going from this line to this line, but if I am here, then I am going from this line to this line. So there is a small problem here, that the problem doesn't really give you the situation. If I am cutting it the horizontally, if I am looking at the horizontal slides, then there is a problem, because this line and then this line, and then I have, when I move down, I'm having this line is fixed, but then I'm getting other line. This is not, so you know the problem is that I have to look at first this piece and then this piece, okay, because for the limits of x it is determined by this as well as this, depending on the values of y. So here it's not a good idea to go about the horizontal slices, but instead you should do the vertical slices, okay, and if you do that, this is what the integral you will get, okay. So this is the part which I was telling you, that looking at the problem, you have to first decide that which way you should cut it, okay, the vertically or the horizontally, so that in one go you can get. Sometimes it may not happen that for example, if somebody asks you to cut it the horizontal slides and compute the integral, then you have to consider two pieces, okay, I'm 2 pieces, 3 pieces, and depending on the problem. So try to do that. So for example, if you consider 2 pieces here, what will happen, and then you can add them up, because this is just the volume, okay. So this is the general idea, that whenever such things, such problems you solve, it's always advisable that you should draw pictures, okay. That's very important. Unless and until we draw picture, we will not get the idea that that how should we compute it, because for example, in this problem I cut this thing and then say that integral is from this to this without really bothering, then I'm going to get a wrong answer and the wrong approach, okay. So you need to be careful, okay. So I'm going to stop here, and then next time we will build on this. So you slowly solve problems and get a feel of how to do things in general.